Research of characteristics of deep cement mixing columns in treatment of soft soil. Abstract: the article presents the content assessment of the application of deep cement mixing technology. From laboratory and field experiments with geological conditions in Duyen Hai, Tra Binh areas, Vietnam, we will find out the factors that affect the quality and durability of the deep cement mixing column. At the same time, we can determine the optimal ratio about content of cement and water for soil samples after being reinforced to meet the economic, technical requirements. Finally, test data is analyzed to serve calculations and simulation based on linear regression models of Microsoft Excel. Keywords: deep cement mixing columns, soft soil, optimal ratio of water and cement, linear regression models. Introduction. Deep cement mixing columns, DCMCs, are the soil at the construction site and the cement is grouted to the ground by the injection grouting pump. The drill bit is drilled down for loosening the soil until it reaches the depth of the soil layer, that needs to be reinforced, then it comes back and moves up. In the process of moving up, cement is grouted into the ground. This is a new technology applied in flooded areas where other types of columns do not meet the requirements. DCMCs are widely applied in the treatment of foundation and soft ground for public construction works such as bridges, ports, embankments, repairing the leaking for the sewer sides and sewer bottoms, retaining walls, reinforcing the soil around the tunnel, preventing landslide of the slope, strengthening the roadbed, bridge abutments, etc. Especially in the Mekong Delta, DCMCs are frequently used because this area is often flooded due to high tides and climate change. With specific advantages in soft ground treatment, the technology of deep cement mixing column is widely used to reinforce the ground, control the subsidence when the work is put into use. The calculation for design of the ground reinforced by the method of DCMCs is based on many different points of view and assumptions. However, based on the specific conditions of soft soil, topography, geological conditions, construction methods, working conditions of DCMCs and experience, the most appropriate calculation method is chosen. In addition, the theory of calculating DCMCs is quite limited. When parameters of durability of the pile are used in calculation, they need to be experimented with each specific soil and construction. 2 research methods. Empirical method, performing experiments in the laboratory and on the site to determine the specific characteristics and factors affecting the durability and quality of DCMCs. Theoretical method, summarizing and selecting experimental data based on linear regression model. 3 testing methods for determining characteristics of DCMCs. A. Parameters of soil and materials used for the experiment. Samples of soil ground used in the experiment were taken in the field of Duyen Hai Thermal Power Plant, Duyen Hai District, Tra Binh Province, Vietnam, which all have the same characteristics of soft gray-brown clay silt. Samples are taken in the field and carefully stored to ensure the natural criteria for the experiment. Parameters of ground soil and materials used for the experiment are synthesized in tables I4. A. Experiment 1. Water/cement equals 1.4. Based on Fig 1, we can see that the value of CHU, kPa, from 7 to 14 days of age increases rapidly by about 70 times compared to the original soil without reinforcement, then it tends to increase slowly until 28 days of age. The intensity of deep cement mixing sample is proportional to the amount of cement in preparation. But when the amount of cement quickly grows from 14% to 20%, the intensity of cement tends to increase slowly. Table B. The result in Fig. 2 indicates that the value of CHU, kPa, in this experiment increases more strongly compared to that of experiment 1, specifically at 28 days of age the value of CHU, kPa, increases by about 137 times in comparison with that at 28 days of age after being reinforced. The main reason is due to the change of the water amount when mixing sample. Compared with experiment 1, in this experiment, when the water amount decreases by 40% when mixing, the value of CHU, kPa, of the sample will increase by 55.24% at 28 days of age. C. Experiment 3, water/cement equals 0.8. Uniaxial compressive strength CHU for mixing sample using domestic water with the ratio of W/C equals 0.8 is synthesized in. Based on Fig 3, it is said that the value of CHU, kPa, of deep cement mixing sample in this experiment increases more significantly than those of experiments 1 and 2. The uniaxial compressive strength of natural soil increases about 211 times at 28 days of age after being reinforced. Similar to the first two experiments, when we perform the experiment of changing the ratio of water/cement on preparing the sample, it will significantly change the value of CHU, kPa, of Dcmcs. Compared to experiments 1, 2, 3, W/C equals 1.4, 1, 0.8, in this experiment 4, based on Fig 4, we find that the value of CHU, kPa, at 28 days of age is quite low. It declines about 36.79% compared to experiment 1, W/C equals 1, 57.82% compared to experiment 2, W/C equals 0.8, and 1.83% lower than experiment 3 with a W/C ratio of 1.4. The main reason is that the water for mixing sample has too high acid content, which is shown in table 4. Then, it facilitates the process of chloride corrosion and sulfate attacking, resulting in the formation of ettringite, sulforaluminate hydrate, 3CaO.Al2O3.3 CaSO4.32H2O, and gypsum, CaSO4.2H2O, softening of cement paste, changing the microstructure to increase porosity and reduce the strength of the deep cement mixing pile. 4. Fig 4. Uniaxial compressive strength of experiment 4. See comparison of laboratory experimental results. Based on Fig 5, we see that experiments with the same type of water, table 3, and cement but with different mixing rates, the results are quite different. Water quality has a great influence on the strength and quality of Dcmcs, so it is impossible to reinforce the soft soil in this area by dry mixing technology. 12. Fig 5. Uniaxial compressive strength CHU of 4 experiments in laboratory. D. Comparison with field experimental results. Based on the results of 4 experiments in laboratory, the ratio W/C equals 0.8 and the cement content of 14% will be the optimal content for mass construction. To verify the feasibility of this option, the comparison with the field results is implemented as Fig 6. 2. Fig 6. Comparison of the value of CHU, kPa, between lab and field experiments. When the cement content is 14%, we see that the result of compressing samples in the field gives higher values than those of experiments in laboratory when the ratio of W/C equals 1.4 and W/C equals 1. With this content, the value of CHU, kPa, of the field results is quite high, but about 35.5% lower than that in the laboratory because the condition of sample preparation in the laboratory is almost ideal. Results of compression in the field also depend on modernity and accuracy of the mechanical system, geological conditions around the reinforced area, construction techniques, etc. Direct shear test. Using the optimal content to determine 0-2 basic characteristics of shear resistance as Table 9. Table 9. Angle of internal friction value from direct shear test. Day. Angle of internal friction. Fig 8. Experimental results and relation between C, kPa, and time. Fig 8 indicates that, at the time of 28 days of age, the cohesive force value of the sample at the rate of 6 to 12% is relatively small, but for the ratio of 14 to 20%, the value is nearly converged and it is not much different, with the average of about 451.89 kPa. This also confirms that the optimal content selected for mass construction is reasonable, meeting economic, technical requirements when investment of the work. The correlation of degree, and C, kPa, at 28 days of age is quite close with coefficient R2 equals 0.8753 and they are inversely proportional when the content of cement increases. 9. Fig 9. Relation between degree, and C, kPa, at 28 days. F. Analyzing experimental data, select results according to linear regression model. Determination of value of CHU, kPa, and summary of results of experiment 3 at 28 days of age are shown in Table 11. Table 11. Summary of results of uniaxial compression test. 111. Comment, selecting data using a linear regression model find that the typical values of Dcmcs are 0.03% lower than the average value. At the same time, correlation coefficient R value is very high, approximately equal to 1, indicating that the relationship of the quantities and results is very close. The error during the experiment is low. 4 conclusions. When reinforcing soft soil ground in coastal area of Vietnam, in the southwest region in general and in Duyen Hai, Tra Vinh area in particular by deep cement mixing technology, it should be chosen with the ratio of W/C equals 0.6 to 0.8, cement content of 14 to 16%, equivalent to 250 to 270 kg cement/m3 of natural soil. This will significantly improve the bearing capacity of soil up to hundreds of times. With the optimal ratio above, the compression result in the field gives quite high results, controlling the product quality and furthermore, ensuring economic, technical requirements. The content and quality of water when mixing samples is one of the main factors that determine the quality and durability of deep cement mixing pillar. Using a linear regression model based on data analysis application of Microsoft Excel software is very useful. This tool helps us retest the experiment process, limit errors, and at the same time increase the reliability of scientific products.